Okay, so we're going to finish up the DSP lecture with the concept of windowing. And as I mentioned in class, windowing is used when you want to analyze a signal, and when you do so, you have to do it in particular chunks, as they call it. Okay, there's different types of windows you can use: hamming or hanning, rectangular. There's a whole bunch, but those are the ones that are pretty common. Most often we use the hamming or hanning window because it's very similar to how the auditory system processes information. So there's an example of a hanning window and a rectangular window. Here's a visual showing you an unwindowed signal, and then when you apply a window to it, it looks like that. In this case, it's a hamming window that's a little broader, a little longer. And so why we overlap them, if you remember, I mentioned that we don't want to lose information and see how this information looks different than this information. And so because of that, we overlap them so we don't lose any of that detail. Again, this was from class, showing you how we basically, this is a kind of theoretical example, but we have an analysis time right there, this first window, and then we overlap it, and then we advance it, and then we overlap it. Okay, typically this is about 50% overlap or so is what we use, so that way we make sure that there is no information that is lost. Now, you may have talked about this in speech science, but there's a concept called linear predictive coding, okay, LPC, filtering is often called, and essentially it's used to take a complex spectral representation. So if we recorded our voices and looked at them, which we will in this semester, there'll be spectral energy at lots of different frequencies. Well, LPC analysis or linear predictive coding helps to take all of that data and make it more manageable. This is used a lot like in telephone lines where you can't transmit all of the energy over the telephone line. So let's look at this for a second here. Oh, the last bullet point where it says pre-emphasis is used to enhance the high frequency components. I think that's important to note because if you remember the let me get a pen here. So if you remember, the speech spectrum looks something like this, and it decreases as the frequency increases. So when you do this analysis, there's something called pre-emphasis that basically just boosts this up a little bit, so it's so it's able to be analyzed. Okay, that's what this pre-emphasis for high frequency components means. So here you have a spectrum of a sound, and if I were to draw the outline, you would get peaks at certain points. Well, we can add this one too. And so instead of using all of this data, right, all of this, the system will extract the value here, here, and here, because that's where the peaks are. Okay. I have some real speech examples. This is another example just pulled offline where you have the red, which is the energy over time, and the blue line essentially represents the LPC spectrum, meaning that it takes all of this, all these detailed points of spectral energy, and it makes them into 1, 2, 3 values. Okay. Here's another example. This is the sound E, and you can tell that because you have an F1 that's low, you have an F2 that's higher, and an F3 that's pretty close to it. And I'm going to do an extra speech acoustics PowerPoint that I'll email to everybody. But the E is characterized by low F1, high F2, high F3. and those are based on the articulatory pattern, right? So it's a high front vowel, E is, and you can tell that just by looking at this. Okay, but here you can see all of the what we call the rough spectral energy. There's a lot of detail. It's a detailed spectral energy. And then excuse me, then we have I want a different color. Excuse me. And then we have the LPC analysis, which is this line. And instead of having all of this energy to account for, now we have three values. Oops. We have whatever this value is, whatever this frequency value is, and whatever this value is. Okay, that's linear predictive coding. Okay, we use it when we analyze the formant structure of vowels a lot, because sometimes it's messy and it's hard to see exactly where the peaks occur, but this this system finds them for us, essentially. Okay, and we'll talk more about it when we talk about speech acoustics. Then the last thing was the spectrograms. Of course, we know what a spectrum is, right? It has frequency down here, has amplitude here, right? We know what a waveform is. Has time down here, has amplitude here. So this is a spectrum waveform. We also have spectrograms, which is a combination of both of these. It shows time at the bottom, and then it shows frequency. So let me draw that here. So you have time at the bottom, frequency here, and then you have the shading, the relative shading, darkness, lightness of the visual as an indicator of amplitude. So the darker it is, the more amplitude it has. So let's look. So here's the spectrum. Here's the spectrum, right? Because it has frequency on the bottom. That's what's on the x-axis here. And it has all those values. If you notice, pre-emphasis was applied because it's not sloping down like this. And that's why because it looks pretty flat. So pre-emphasis was surely applied to that. So here you have your dynamic information, right? You can see the formant structure. That's not really flat, but you can see there's all the dynamic information. So if you were to change the place, like if you were measuring right here, you might get this output. But if you measured here, this would look different because your energy is at different points. Okay. I don't know how to erase that, but I'm going to go back. Oh, it didn't erase. So anyway, but this is the spectrogram right here. And I wanted to point out the dynamic components of the spectrogram. So we talked about narrowband and wideband or broadband spectrograms. In digital signal processing, there's always a trade-off between viewing time information or temporal information or viewing frequency information. You can't have the best of both worlds. You can't see really finite frequency information, but also have very good access and visualization of time information. Okay, so narrowband uses long windows for high frequency resolution but low temporal resolution. So narrowband spectrograms, the windows are longer in the recording, which gives you good frequency resolution but bad temporal resolution. And the converse is true for wideband spectrograms. Very short analysis window gives you very good time resolution but poorer frequency resolution. So if you're trying to accurately capture these temporal events like formant transitions like we just saw, stuff like that in a spectrogram, the wideband spectrograms are better. And again, we'll look at that. So here in this wideband, if you just imagine that this yellow line wasn't there, you would be able to see this transition very well, right? Here, without it, I know it kind of seems like it is easy because it's there, but it'd be a little more difficult to see that format transition. But you can see the fundamental and the harmonic structure. Sorry, I can't overlap those. But you can see frequency, energy very well. That's what this is. You can see the individual harmonics. So narrowband, you get very good frequency information, and wideband, you can see temporal or information over time a little bit better, or much better, but you can't see the frequency content as well as you could with the wideband. So that just highlights the trade-off between viewing temporal or time information and frequency information. And we'll go over this again. We're going to talk about speech acoustics, so we'll cover that again. And here's the last example. Here you can see the same thing. You can see in a narrowband spectrogram you have very good frequency, right? You can see all those. Can't see those up here, right? But technically you can see the format transitions better, although this is not the greatest of a visual for that, but it does show you frequency, being able to see frequency information versus information over time. All right, that's it on DSP, and we'll chat about it more in class.